make a quick, as usual, review of what we did. We started with a one-dimensional vector space with a basis. Therefore, we identified it with E1, and then we, on this space, we consider the coordinate function that we use, that we denote indifferently, like x or xe1, with values in the real number. And this, to every vector, it associates the component of this vector in this basis. Now, from this, we have formed the polynomial algebra, which depends on x, but we simply use the notation p, which are all the complex polynomials, and this is purely algebraic. Then we have introduced statistics by putting a probability measure p on the real line, and for us, probability measure means probability with all moments. This symbol means all moments. Therefore, x becomes a random variable. But to give a probability is almost equivalent than giving a state. On P, and essentially, and therefore we restrict to states on phi. When we give a state on phi, we have a scalar product, and remember that the scalar product that come from the state are characterized by the property that x, the multiplication by x, is a Hermitian operator in P, considered as a Hilbert space with this scalar product. Once you have the scalar product, you have the basic, you construct, with the procedure that we did in the previous two lectures, you construct what we called a three-diagonal structure. What is a three-diagonal structure? I recall you what is our definition of three-diagonal structure. Three-diagonal structure is given by three ingredients. One ingredient, three-diagonal structure on P. It is given by three ingredients. Ingredient one means that P considered as a vector space. Remember, when we consider P as a vector space, we write P times phi 0. So P, considered as a pre-Hilbert space with this scalar product, is decomposed into an orthogonal sum of one-dimensional spaces, and in our case, we know that these one-dimensional spaces have a special structure. They are the multiples of the monic orthogonal polynomials. They are the multiple of the monic orthogonal polynomials. And therefore, so this is the first ingredient. There are three, and it is very important that you keep all three in mind. So, first ingredient is the orthogonal decomposition. The second ingredient is that we have a certain what we call the creation map, that go to every vector v in the complexified of C. I will not speak of complexification. If there are questions, maybe additional questions, we discuss at the end, or maybe we do a separate session for questions. So to every vector, I associate a certain operator A daga V, which is a linear operator on operator is gradation increasing by 1. Which means that the nth space is mapped into the n plus 1. The property is that in fact, for each V, this is A is a map from V, the complexified, to the linear operators. When I consider A in a single vector V, then I have a certain linear map on P. Okay, this is gradation increasing. And AV for every V is adjointable. And most important, then we have A0, which is self-adjoint and gradation preserved, which means that Pn is mapped into itself. So you understand that the crucial point is this, that if I have a creation operator, then annihilate, this is the is adjointable, and we denote the adjoint, we denote A minus 3. So, as you see, the crucial point is that I have a creation, because then, by the condition that the annihilation is adjoint, I deduce the annihilation. So, this is an important condition. As you see, this is a separate condition. Now, let us separate the first 3 conditions, and let us use them to give a general definition. Now, I replace the special polynomial algebra by an arbitrary pre-Hilbert space. So, my starting point is a vector space V. It can be real or complex. In the case of orthogonal polynomial, it's complex. It's the complexified of V. But I take V, a vector space, and I don't specify if real or complex. Other cases we don't consider. Then I define an interacting Fock space on V by the following prescription. An interacting Fock space is,
so V is Hilbert space or just a vector space?
What?
V is a Hilbert space?
No, vector. Just a vector space. An interacting Fock space on V is a Hilbert space, a pre-Hilbert space. I want to work, remember, in pre-Hilbert category. A pre-Hilbert space, which is given as a pre-Hilbert space, is given by a gradation, an orthogonal gradation. And this orthogonal gradation is made of pre-Hilbert spaces, each of which has its own scalar product. You see, as you see, I am abstracting from this definition. But historically, the history went in the opposite time direction. First, this was introduced, and later on we recognized the bridge with orthogonal polynomial. But from orthogonal polynomial, it comes very natural, this definition. So this is condition 1. Let us call it the axiom 1, interacting Fock space 1. Then, interacting for space 2 is there exists a map, and here V plays the role, a linear map from V into the linear adjointable operators on the Hilbert space H, and I put the scalar product to emphasize that adjoint is with respect to this scalar product. Okay? And the third fundamental property, this map must have this property. We require a minimality condition, which can always be assumed. This is a minimality condition. I want that A, V, I write A capital V. You understand what it means? It means the set. Well, I will write this piece. A capital V of H n is equal H n plus 1 for each V in the vector space V. This notation means simply that this is the set of all A daga H n when V arbitrarily varies in V. It is a very simple exercise to prove that this set is in fact a vector space.
You mean for every n in vector?
For every n in n.
Yeah, not V.
This gradation generalized the annihilator. This is essentially annihilator. Creator. Okay? Then
Not for every V.
there is another condition that I forgot to put. We want a special property for the zero space, which also reminds that zero space is the zero space is just one dimension, complex dimension one. And let us call phi because the fact that the norm of phi is 1 uniquely fixes the scalar product to be the standard Euclidean scalar product on C, which means Z scalar Z prime is Z conjugate times Z prime.
Yeah, but I don't think you have for every V. You don't want.
Not for every V, capital V. This is capital V. This is just a notation, is it?
Yeah, no, but on the right hand side you have written just after that. You have written for every V.
This is wrong. For every V is here. Yeah. Okay. Capital V is the set, is this set. So it doesn't depend on a single V. Okay. And it's an exercise to prove that this is a vector space. A minimality condition simply means, because I can take, if it is smaller, I just throw away the path, the orthogonal to this subspace, and I reduce to a situation in which this is satisfied. So this is not such a big issue. And so that's all, because the adjointability condition means that this is adjoint. Pay attention, as Hilbert space operator. So the existence of adjoint means, and I will denote the adjoint of this for the scalar product, I will call the annihilator. Okay. Now this condition implies, you see, if you apply by induction this condition, now we are not doing any assumption on the dimension of V, and therefore we are not doing any assumption on the dimension of the Hn. Typically we have infinite dimension, okay? However, now, so you see, by assumption, I have that this condition, that essentially the creator shift automatically implies, this condition automatically implies that the annihilator kills the vacuum. Because you see, whatever the vector C is here, the annihilator acting on the vacuum, phi, we said in more general, will give something of the form a daga C. So if an adjoint of the annihilator exists, it must satisfy this condition. Now, since whatever is this vector, whatever is the vector C, because of this property, there can be no component on the zero vector space. So it means that this vector A minus phi annihilates the scalar product with all vectors of the space, included itself, and therefore it must be of norm zero. So, since we are identifying object up to vectors of norm zero, we can take that A daga phi is equal to zero. Okay? We know that it has norm zero in any case, so we will put it equal to zero. In Hilbert space, this is not an assumption, but it's so now, you see, we start from phi 0, and then we form A daga V1 phi. And we know that the set of all these vectors, phi, we start with phi, and then set of all these vectors is exactly H1. Then, since this will, it means that if I consider the vector AV2, AV1 to phi, they will give rise to AH2, and so on. So in other words, I have that the vectors A daga Vn, A daga V1 phi are a linear basis of the full space. So it's a system of generators. Remember, we are in pre-Hilbert space, so we are not taking infinite sums. They are a system of generators. Now, this is an important point, because this gives you the idea. You see, if you consider this expression as a function of V1, Vn, this is a multilinear function. And since it is a multilinear function, by the universal property of tensor product, I know that there is a unique map, and that there is an homomorphism of the nth tensor power of V into onto Hn. This is a general property of pre-Hilbert space. Okay? Because it's the universal property of the tensor product. The universal property means that if I have a multilinear, n-linear map from V to a certain vector space Hn, then I have a linear map from V to Xn, and I have an homomorphism onto Hn, which is the linear map. A linear map which essentially intertwines, which means that I take T of, in my notation, V n tensor V1. This is equal by definition A daga Vn, A daga V1. So this is well defined for each n tuple. And the universal property of the, I mean, if you want to prove this, for example, you can take a V finite dimensional, develop it into a basis, then this V1 Vn will be a tensor product of element of a basis, which is a linear basis of the tensor product. And so, when I have a linear basis, I can define a linear map arbitrarily. This is an universal property, is an intrinsic way of saying this very simple fact, okay? Now, I have this map, but since I put a T without a dependence on n, because I consider this as a restriction of the full tensor algebra to the nth part for each n, okay? Now, since Hn on Hn, there is a scalar product, which is what we call the scalar product of, the scalar product dependent on n, okay? So, by using this T, I can define a scalar product on this tensor power, because I simply define Un tensor U1 scalar Vn tensor V1 is by definition, so I will define this new scalar product. Let us call it this is delicate. I don't want to use the tensor symbol here. Let us call it also n, because in practice it's the same. And by definition is this A daga. Essentially I use this